This is problem number 5 from assessment number 6. It says solve the equation for theta in 0 to 2 pi. Now remember, 0 to 2 pi just means one revolution around the circle. They want to know the solutions for theta, the angles, for one revolution around the circle. And the reason they say one revolution is because every time we go around the circle, we learned about coterminal angles, we're essentially getting more coterminal angles, which are the same angles, but just more spins, that can be solutions. And so we end up with like an infinite amount of solutions if we just keep spinning. So they're saying just one revolution, we want to know the solutions for just one. Now the problem is sine squared theta equals 1/2. I want to write this in a different version just real quick. If I subtract 1/2 to the other side, I get sine squared theta minus 1/2 equals 0. You'll see the problems start like this quite often, sometimes even with a leading coefficient of like 4 or something like that. Just realize that your whole goal is to isolate the sine theta, which means you need to add the 1/2 over, which would take you back to our original problem. And then if you have a leading coefficient, you would want to divide that out. So you want to do those steps first, just like a normal algebra equation. So we're going to add the 1/2 over. That's sine squared theta equals 1/2. And then at this point, once you get the sine squared theta isolated, you can actually start to manipulate this problem, the squared part, to finish the problem out. So sine squared theta usually throws students off. They don't realize, that the square is meaning that it's sine theta squared. So I like to always write this as sine theta squared before I do my square rooting, because you can see now, all right, I need to square root this and I'm left with sine theta. If I square root the left side of the equation, I get sine theta squared, root of sine theta squared equals plus and minus the root 1/2. This will give me sine theta is plus and minus, and I can split this root between the 1 on top and the 2 on the bottom. So this means I have sine theta equals plus and minus root of 1 is 1, so it's 1 over root 2. Now at this point here, that's when I want to start to find my angles, and my angles that correspond with the sine function. I go to my unit circle, but you'll notice when you go to the unit circle that 1 over root 2 is not written anywhere on here for distances, right? 1/2 root 3 over 2, root 2 over 2, root 2 over 2. It's not written anywhere on any of these coordinates. And so what do? I can't find the angles if I don't have one of these distances. Well, what if you notice the bottom, the denominators, all the denominators have been rationalized. So that's really what you have to do next, is rationalize this denominator. You got root 2, which makes it irrational. So you want to rationalize it by multiplying by root 2 over root 2. And that's going to give you sine theta equals plus and minus. And when you multiply 1 times root 2, you get root 2 over, and root 2 times root 2 is root of 4, which root of 4 is, we know to be 2. And now I have plus and minus root 2 over 2. So if I look over here, I can see root 2 over 2, that's the 45-degree angle. So sine, when is sine root 2 over 2? Well, that's at 45 degrees. That's also at 135 degrees. So that's where it's positive. So we can write theta equals 45 degrees and 135 degrees. But it also could be negative. Well, down here we have negative root 2 over 2 for sine, which is the y part of the coordinate. That's at 225 degrees. And then also at 315 degrees. And so our answers for the problem for theta are 45, 135, 225, and 315, because those are the basically the 45-degree angles in the different quadrants. Now, they say 0 to 2 pi. That tells you they want it in radians. So I wrote them in degrees. Really, they want them in radians. So we could write theta equals 45 degrees, we know is pi over 4. 135 degrees is 3 pi over 4. Let's see. 225 degrees is 5 pi over 4. And finally, we've got 315 degrees, which is 7 pi over 4. So our solutions are right here in radians.